So for this video, we're going to focus on the exponential and logarithmic function here. So we're going to focus on how do we convert from logarithmic to exponential, exponential logarithmic. How do we evaluate logs, right? So we're going to go through a few examples of that. We're going to solve some basic log problems, talk about the domains of logarithmic functions, and then do a quick sketch of a graph for a logarithmic function here. So the first thing that we're going to start with is converting back and forth between logarithmic form and exponential form. So we have logarithmic form right over here. Y is equal to log base b of x. And this is equivalent to its exponential form, which is b to the y is equal to x. So one thing that we need to understand in working with logs is that the logarithmic and exponential functions are inverses of each other. So a lot of times, like let's say, for example, later on when we get into solving logarithmic equations, right? Solving logarithmic equations in this form is, very difficult here. So when we're given something in logarithmic form, one of the first things we're going to do is convert this over to exponential form, because as in exponential form, it's a little bit easier to solve. So we're going to need to convert back and forth between the two. So if you're not too familiar with the logarithmic form here, so quick little explanation here. So you might be given examples that look something like this, right? 9 to the power of x is equal to 15. Now, this value of x here is going to be some, difficult decimal more than likely here, right? 9, we know that 9 to the first is a 9. We know that 9 squared, 9 times 9 is an 81. Right? So that means that x has to be somewhere between 1 and 2. But calculating that by hand, it makes it almost impossible here. So when we have something like this situation here where we're trying to solve for x, logs help us in this situation. And what we tend to do here is we tend to take the log of each side, or the natural log of each side. And what that allows us to do is it allows us to take this x and bring it down in front as a coefficient using our logarithmic rules, so that we have everything in one line that makes it a lot more solvable here. All right, so we go back and forth a lot between logarithmic and exponential, exponential and logarithmic, just depending on what we're being asked to do. So let's work through our conversions first here. So our first three examples, we're going to go from logarithmic to exponential. So I always say pay attention and compare it to the property and compare here. Right, this 2 is where this y is, right? So 2 would be our y here. And that is equal to log base b. So that means this 5 here is a b of x. So x is just an x. So to convert, we just need to mirror this form here. What we want to do is we want to take b, which for us is a 5, right? That's going to be our base. And we're going to raise it to the power of y. Well, for us, remember, y was a 2. So this is going to be 5 squared is equal to its x. Remember that this x here was in this x position, so it's just going to equal x like that. We're not going to simplify this. We're not going to solve this. This is asking us to convert it, so this is the logarithmic form. This would be its exponential. Let's do that again, right? So here with this one here, again, match it up to the logarithmic form. This 3 would be our y, and that is equal to log base b. Now, b is just a b here, right? So this b is this b. 64 is going to be our x. All right, so in order to convert, it is b to the y. So our b is just a b to the y, which we got a 3, is equal to our x, which is a 64. And let's do this one more time. So again, match it up. Y equals, so y is a y, is equal to log base b of x. And when we convert it, it's going to be b to the y is equal to x. Right, so that's how you go from logarithmic to exponential. Now let's do the reverse. Let's go from exponential to logarithmic. So let's compare that. We're going to start with the exponential form right over here. Right, exponential form, this is our b to the y is equal to the x. Now go backwards. We need to create this. So we need to create y equals, our y is a 2, so 2 equals. Log is always going to be there. Log base b. Now our b is a 12, and then that's going to be of x, which for us is just an x. So that is our logarithmic form there. Let's try that again. All right, example E. Again, base is your b. All right, so this is our b. Raised to the power of y is equal to the x. So when we convert that to logarithmic here, y equals, so 3 equals log base b of our x, which is an 8. And one more time here, again, matching up to exponential form, right? Our base here is our b, right? So that's going to be an e. Y looks like it's just going to be a y, and that is equal to the x, so 9 is an x. So when we convert, this needs to be y equals log base b, our b is an e here, of x, which is a 9. So when we evaluate logs, right, so we're given here log base 2 of 16, and we need to evaluate this and figure out what this actually equals to. All right, so it's given to us in logarithmic form, so the first thing I do is match it up to the logarithmic form. And I have log base b of my x. The only thing that's missing is the equals y. So keep in mind that that is what we're solving for. We're trying to figure out what this equals, so go ahead and just set it equal to y so it's in proper form. Now, first thing that you want to do here is convert this to exponential. So we're going to convert this to exponential just like we did up top here. So we have our log base b of our x is equal to y. So when we convert, keep in mind that is 2 to the y is equal to our x, which is a 16. So you can evaluate logs one of two ways. The first way, just using mental math, and you can figure it out, like you could in this example here. 2 to the y is equal to 16. Well, 2 to what power is 16? We know 2 to the first is 2, 2 squared is a 4, 2 cubed is an 8, and 2 to the fourth is a 16. That means y would have to be a 4 in order for this to be true, right? Since 2 to the fourth is equal to 16. One other rule that we can use here is called the same base rule. And the same base rule says that if you have b to the m equals b to the n, so your bases are the same, right? So think like 2 to the x is equal to 2 cubed, right? So it says as long as your bases are the same, you can set your exponents equal to each other, right? It says then m is equal to n. So just real quickly that example, so like if I had 2 to the x is equal to cubed, if the bases are the same, you can set the exponents equal to each other, so x would equal to a 3. You can use the same concept here. So we had 2 to the y is equal to 16. A secondary way that you can look at this using the same concept here is getting these bases to be the same number. Now it's easier to turn a bigger number into a smaller number, so I'm actually going to drop down the 2 to the y, and I'm going to do a substitution here. I'm going to say that 16 is 2 to the fourth, right? Because it is. 16 is 2 to the fourth. Which means now I can use the same base rule. My bases are the same, so you can take your exponents, set them equal to each other, and y would be a 4. All right, so sometimes you can hash it out mental math way. Sometimes you may want to use the same base rule. Kind of just depends on what you're given. Here with example H, let's look at this. We have log base 7 of 1 over 49. First thing I'm going to do is set that equal to y and convert that to exponential. So keep in mind it's going to be your base. So 7 to the y is equal to 1 over 49. Now, we want to try and get the same bases here, right? So the first thing I want to do, I see that I have a fraction here on the right side. I want to get rid of that fraction, and I want to make it a regular integer. So essentially, I want to bring this 49 and bring it up to the numerator. You can do that by using the negative exponent rule. You can bring that 49 up to the numerator by changing the power of the exponent. Keep in mind this is technically 49 to the first, so I can bring this up top by making that 49 to the negative first. This 7 over here to the y, I'm just going to drop down. Now, I need to make these 7s, right? I have a 7 here, and I know that I can easily turn a 49 into a 7 because 49 happens to be 7 squared, right? And that 49 was raised to the negative first, so this 49 here is still raised to the negative first. I'm just going to drop down the 7 to the y on the left. Now, I almost have a 7 as my base here, so I have 7 squared then raised to the negative first. Keep in mind when you have an exponent raised to an exponent, you need to multiply those together. So here, this is 7 to the second, then to the negative first, multiply 2 times negative 1 to make that 2 to the negative 2. Drop down 7 to the y on the left-hand side. Now this gives us the same exponents. That gives us the same bases here. We have a 7 here, which means we can use the same base rule to set our exponents equal to each other, which means y is equal to a -2. It does help if you do know your exponent rules when it comes to these problems here. So if you need a refresher, go back and look at power rules for exponents, maybe the negative exponent rule. So you want to look through your polynomial exponent rules and maybe refresh that if any of these rules here were a little bit confusing. Moving right along, here we have log base 25 of 5, and we're going to set that equal to our y so that we can convert this to exponential, which means base, the 25, raised to the y is equal to the x, which is a 5. So we need to figure out 25 to what power is equal to a 5. So we're going to use the same base rule here to help us. So it's always easier for the bigger number to go down smaller. And I know that 25 is 5 squared. And I'm going to take that 25, it was raised to the x power, and that is equal to 5 technically to the first. Now we do need to clear up this exponent right over here on the left-hand side. Again, a power to a power, you multiply. So we're going to multiply 2 times x, which is just going to give us 2x. And that's going to equal 5 to the first. Now we have the same bases, which means we can set the exponents equal to each other. That means 2x is equal to a 1. Solve this equation for x by dividing by 2, and you get that x is equal to a 1/2. Moving on to our next example, convert this to exponential, so set it equal to y. Base, so little number, raised to y is equal to your x, which is the 5th root of a 2. Now, one of the first things we're going to want to do here, anytime you're given a square root, cube root, 4th root, a radical here, you want to go ahead and convert that to its exponential form. So keep in mind that the square root of x is x to the 1/2. Cube root of x is x to the 1/3, and so forth. 4th root is x to the 1/4, 5th root x to the 1/5, and so on and so forth. So I'm going to drop down 2 to the y on the left. The 5th root of 2 is just 2 to the 1/5. That is what a 5th root is. Right? Taking the 5th root of the number is the same thing as taking that number and raising it to the 1/5 power. So just by converting its radical form to its exponential form here, it already makes our bases equal to each other. So we have a 2 here, we have a 2 here, which means we can set our exponents equal to each other, and y is equal to a 1/5. Our next set of examples here, we're going to solve the basic logarithmic equations here. In solving these logarithmic equations, our first step is going to be convert this to exponential. Almost always when you're working with logs initially, you're going to want to go ahead and convert them to exponential and then solve them in that way. So let's convert this to exponential. So keep in mind, same way that we've been doing here for the last few examples, you're going to take your base. Right, you're going to raise it to the power of y, which is a 2, is equal to the x, which is an x minus 5. Solve this equation. On the left-hand side, we have 3 squared, which is a 9. Drop down the right-hand side and solve that for x by adding 5 on each side. And we get that x is equal to a 14. Next example, again, logarithmic form, you want to convert it to exponential. So your base, 5, raised to the y, right, what it's equal to, is then now you're going to set that equal to the x here, which is the 625. So 5 to what power is 625? So you can mess around with this in your calculator a little bit. And 5 to the 4th power is actually 625. All right, so since 5 to the 4th power we know is 625, we can either automatically set x equal to 4 based off of that, or we can use the same base rule and use the same concept. 625 is 5 to the 4th, which means we now have the same base. You can set your exponents equal to each other, saying that x is equal to 4. Last example here, convert to exponential. So your base, raised to the power of x here, right? What it said equal to. So it's base to the power of this set equal to this is always how I remember that. So 3 raised to the x is equal to 1 over 243. So I'm going to go ahead and do a substitution here. So I know that 243, so that's actually 3 to the 5th power. So I'm going to go ahead and make that substitution here. I'm going to drop down 3 to the x, and I'm going to call this 1 over, well, 3 to the 5th, right? 243 is 3 to the 5th. Now, I need to have the same bases, and I don't have that yet. So we did a similar problem to this, where you want to take your denominator and raise it up to the numerator. And you can do that by using the negative exponent rule. You can bring the denominator up top by changing the exponent sign. So this is now going to be 3 to the negative 5th, which means my bases are the same. We can set our exponents equal to each other, and x is equal to a negative 5. So let's get into how do you find the domain of a logarithmic function. So in a nutshell here, what this is stating here, in order to find the domain of a logarithmic function here, you're going to take the x portion, or what they've done here is they've put in g of x. But that's really just this x part here, x minus 5, the 625, the 1 over 243, right? What's been in this x position here that we've been talking about with this whole video. They've just called it g of x instead, because it could be a single x, it could be a single digit, it could be a polynomial, or different things like that. But according to this, right, if we have our function f of x is equal to log base of a g of x, what you want to do to find the domain is take that g of x and set it greater than 0 and solve. So here our g of x is an x plus 3. Set that greater than 0 and solve, which means we're going to subtract 3 on each side. So x is greater than a negative 3. If you want to draw a line graph to have a visual, you most definitely can. If we want everything greater than 3, we want everything to the right of 3. Which means, keep in mind, when you find domain, your answer should always be in interval notation. So the domain here, start with your parentheses, right? Because of your symbol, it can't actually equal that negative 3. From negative 3, and we want everything greater than it, so it's going to go off to a positive infinity. Next example, again, take your g of x. Here it's an x minus 7. Set it greater than 0 and solve. Add 7 to each side, and x is greater than 7. Interval notation here, parentheses on the left. Everything greater than 7, so we want 7 to positive infinity. Last example here for this video, we're going to use the graph f of x is equal to 3 to the x in order to graph g of x is equal to log base 3 of x plus 4 minus 5. So it says first use the graph of f of x is equal to 3 to the x. So typically what we do in graphing logarithmic functions here is we take a look at its exponential counterpart. And if we have log base 3 of an x, that would convert to 3 to the x here. So what we're going to do, because these are inverses of each other, right? So exponential form is a inverse to its logarithmic form. Logarithmic is an inverse, right, with the exponential form. So what we do when we graph logarithmic graphs is we take a look at its exponential. We invert that graph and then apply our transformations of the given function here. So graph 3 to the x, or at least get points of 3 to the x, right? So it says use this graph, right? So if I plug in values for 3 to the x, right? So let's just say I'm going to plug in a negative 1, a 0, a 1, and a 2. And do 3 to the negative 1, 3 to the 0, 3 to the first, 3 squared. Plug in these values. 3 to the negative 1 is a 1/3. 3 to the 0 is a 1. 3 to the first is a 3. And 3 squared is a 9. So what you want to do, these are the points on f of x is equal to 3 to the x. Because these are inverses of each other, I want to find the inverse, which means I need to flip-flop these points. I need to change their positions. X is now y is now x here. So this is what my points would look like. All right, so what I like to do here, so what I'm going to do is I'm going to use this black marker. I'm going to go ahead and plot these. This is not this graph. It's very, very similar. These points here would represent g of x is equal to log base 3 of x is what these points would represent. I'm going to go ahead and plot these here. So that means a positive 1/3, and then a negative 1 would be somewhere around there. 1, 0, 3, 1, and then 9, 2 is what that graph would look like. And I'm going to connect this lightly. This is not our graph. All right. But what we need to do, taking a look at transformations of a logarithmic function, keep in mind inside the parentheses by the x, that is a horizontal shift. A +4 actually means left 4. At the very end of the equation, this -5, you can kind of almost think of that as a y-intercept with, slope-intercept form. This -5 is a vertical shift, so it means down 5. So this graph here is going to be the same as this one that we just did, but go left 4, down 5 because of these transformations. So I'm going to take every point here and go left 4, 1, 2, 3, 4, down 5, 1, 2, 3, 4, 5. Same thing for the rest of the points. Left 4, 1, 2, 3, 4, down 5, 1, 2, 3, 4, 5. Right, left 4, 1, 2, 3, 4, 1, 2, 3, 4, 5. And last one, left 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, somewhere around there. Connect the dots, and that is what this graph here would look like.